Hello, my name is Murilo Gossinelli. I'm an AI engineer at Intel, and I'm here today with Ben.
Hello, yeah, I'm also an AI engineer at Intel. Happy to be here.
Awesome. So Ben, today we're going to be walking over a application on using LLMs for drug discovery use case, which is something that I've never done before. So I'm excited to dive into this and show you guys what I came up with. And for this demo today, what I'm going to be going over is going to be a few key things. One's going to be LobeChat, which is basically this application that I have open here, but it's basically just an UI interface that developers can interact and use many different LLMs. So as long as you have an API key, you can use your API key in that platform, and it's basically an aggregator. So you can use LLMs from many different platforms. And we're also going to be going over the enterprise inference project under OPIA. Basically what enterprise inference is and how you guys can use the API endpoints there. And then we're going to be going over a paper on using LLMs for drug discovery use cases, where I got a lot of inspiration for creating this application today. So without further ado, let's get started. I have here the LobeChat GitHub repo. This is a repo that gained a lot of popularity recently. As you guys can see, has 62,000 stars on the repo. And if I scroll down, you see there is some things about what it is, but basically this is just an UI. It's basically a framework that you can use many different LLMs as long as you have their API keys. It's basically an aggregator for LLMs, so you can chat with them, and it's a centralized place that you can use whatever LLM that you like.
Is it kind of similar then to like a ChatGPT, but you build it yourself, or?
Yeah, that's correct. So it's similar to ChatGPT, but you can use any LLM that you want. And I'm going to talk a little bit about that in the application itself. So let's head to the application. So basically, this is what LobeChat looks like. And you can see that there's a chat here on the bottom. You can select different LLMs that are available over here. So you can see we have some OpenAI LLMs. We have Meta, we have Ollama, DeepSeek, and Queen. So I'll show you how to see them. Here on the right, so you're going to see your chats. This is where they're going to be stored. But to see the API and where you can use your LLMs, you're going to click here on the upper left corner and go on settings. And then you're going to go on AI service provider. And you see that you have many different options available for many different LLMs that you like to use. So right now I have selected OpenAI and Ollama, but you also have available Microsoft Azure, vLLM, Anthropic Claude, Amazon Bedrock, Google Gemini, DeepSeek, Hugging Face, and many, many more. So if you have an API key from any of those platforms, you can just use your API key here, and you'll be able to have a bunch of different LLMs or services that you may use aggregated and centralized in one place.
It's pretty comprehensive, because a lot of the other, I guess, tools that I use, they don't have this many ways of connecting your models. So there's quite a few here.
Yeah, exactly. It's quite comprehensive. You have a lot of different options here. So for us right now, we're going to talk a little bit about the Intel AI inference, which if you go here, this is going to be the main enterprise inference repo that is hosted under the OPIA project. So it's github.com. Well, I'll link the repo below so you can find all of that information there. But basically, this is what the enterprise inference is. We have Gaudi accelerators hosted on the cloud, and we have LLMs in the cloud as well, that they're going to be, basically, you're going to be using Gaudi to do inferences on those LLMs.
Also, you have Xeon in that image. So that looks like there's some LLMs that, yeah, you could host on the CPU Xeon.
Yeah, exactly. Good point, Ben. So yeah, we do have some Xeons as well, and Gaudis as well. So not only Gaudis, we also have Xeons. And talking about one of the cloud providers, we have Denvr Dataworks, where Denvr has Gaudi 2s on their platform, and they have a big family of models that they provide here. So all of those models are available on Denvr, and today we're going to be using Llama 3.3, 70B, I believe. So yeah, so going back to the application, to LobeChat, we're going to click on OpenAI because the API endpoints from Denvr Dataworks and the other API endpoints that we have available on different clouds, they are OpenAI compatible. So there's three things about the APIs that you guys want to know. Number one is the API key. So you're going to get an API key. You're also going to get an API proxy URL. And the third thing is the model name. So the name of the model that you're going to be using. So here, like I said, we're going to be using Llama 3.370B to basically chat with the model on LobeChat.
Yeah, and I was just going to point out that this URL you have showing here, that's like the model endpoint URL, and you might recognize that it looks kind of similar to the OpenAI endpoint. It's just instead of putting OpenAI, we're putting like inference.denvrdata.com, but it's still the same like chat completions API calls that are happening, just to a different endpoint.
Exactly. It's basically the same. So it's very compatible with the platform. I already have everything here entered on the platform. So we can actually go to the chat tab and we can start chatting with our model. So to select our model, I'm going to go here and I'm going to select Meta Llama 3.370B instruct. That's the name of the model that we passed. And then I can ask any question. For this particular use case, before asking a question, as I said previously, today's going to be about using LLMs for drug discovery. So we came across this paper recently that is titled Large Language Models in Drug Discovery and Development from Disease Mechanisms to Clinical Trials. If we click here, we can see the entire paper. And it's a really awesome paper. It was released or published or submitted to archive September 2024. And it basically just walks through using LLMs in the process of drug discovery. And there's many different use cases, but right now this is basically, they identify the past use cases, the current use cases, and then future use cases of how LLMs can be used in the drug discovery development. And today we're going to be focusing on using LLMs for clinical trials or doing some clinical trials modeling using LLMs.
Yeah, on the left, when we were going through this paper, there's kind of these 3-stage process: understanding the disease mechanism and the things that go with that, the actual drug discovery, and then the clinical trials that you need to have when you have maybe identified a potential new drug. So yeah, like Merlo was saying, we were going to look at this LLM's automatic patient trial matching. So yeah, on that right-hand column, you can see all the ways that LLMs are proposed to be used.
Yeah, that's correct. That's right. We're going to be looking exactly at that. Thank you, Ben. So going back to the application, now that you guys have an idea what we're going to be doing, I'm going to be actually putting a prompt here that I already have copied, and I'm just going to click send.
It's quite a long prompt.
Quite a long prompt. Let's go a little bit about the prompt itself. So we're going to be prompting the LLM saying that you are an highly experienced AI researcher in biotech, and we're going to try to propose a novel application. It's going to be completely written in Python, and we want to leverage LLMs for a specific point in the drug discovery pipeline, which, in this case has 3 main stages: the understanding, the disease mechanisms, the drug discovery, and the clinical trials. So basically the things that Ben was saying previously, we just gave more or less the high level definitions or the high level idea of what we want to do based on the paper. And then, of course, the prompt kind of explains what each of those things are and goes more into detail. But then here at the bottom, we say, please include a short project title, a 1-paragraph summary of the application, the LLM technology that is going to be used, the specific task, the input-output format of the data, and so on and so forth. And also a requirements.txt file with all of the Python libraries that are going to be required to run this.
It's important when we're doing these prompts to really think through what you want and to spend some time looking at what are the requirements that you have for this model, and you can save some time of less back and forth with the LLM by providing very clear criteria like you did there.
Yeah, exactly. So the more detail and information that we provide about what the output is going to be, the better. It's going to be much more specific. Here we have the project title, we have the summary, we have the LLM technology. So we're going to be using Hugging Face transformers and some task improvements, automation, potential challenges and solutions. And then it gave us a bunch of Python code, pretty extensive code actually, that we could try to run this.
Yeah, it looks like it gave some data there at the end too, some like synthetic data.
Yeah, I believe he gave us some, he basically made some dummy data here at the end. So basically we could try the application that he gave us, because it's not super easy to get clinical trial data, right? So he basically generated some data that we can get up and running pretty quickly. And also he gave us a requirements.txt file and then some code as well for a web UI interface. Here he's using Flask and Django. I would rather have using Streamlit, but I should probably change the prompt to that if I'd like, or simply chat here with LLM and say, change the UI for Streamlit. And yeah, he gave us a lot of code. Before I dive into the code, Ben, would you like to point out anything about this?
Yeah, no, I think just the it's nice that it provided the requirements file like we asked with the all the libraries that are being used, and when if you can just scroll up a little bit, walk through just a couple of the functions, what it came up with.
Yeah, sure. So the first function, it basically is just fine-tuning the model, and we need some training data for that. So that's why it generated that dummy data. And then it's initializing a class inside the function, which that's kind of weird.
Yeah.
Patient trial data set. So it's using PyTorch for that. And it creates a torch data set and then also a data loader.
Yeah, sometimes the format of the code that it comes up with is maybe not ideal or what you would actually use in real life, but it's helpful to get some ideas for sure.
Yeah, exactly. So yeah, then he's just basically fine-tuning a model. He uses Atom as the optimizer for finding the best weights during the training process. And here has the validation step. We're reading the validation data that does not exist. So yeah, it just basically, the way how I see this is that it gave me a bunch of code that I'm sure if I try to run this, it's not going to work. But it gave me some ideas to get started, which the main ones was basically trying to find a model that was perhaps already fine-tuned for clinical data or clinical trials. And then we also have here a match patient function that is basically does the matching between the trials and the patients. And here at the bottom, you just gave some example usage and then some example data sets. And it creates the data set and then calls the fine-tune model function. Okay, so let's actually dive into the code. So as you can see here, you notice the code looks a little bit different than the output from the prompts, which is okay, but it just gave me some ideas on how to get started. I have actually built a repo that is going to be available. It's going to be on the link of the video as well. And you have access to all of the code that I'm going to be showing here today. But basically, I have this notebooks folder, and then I have 4 main notebooks. I have a explore dataset, simulate trials, patient trial matching, and enhanced patient trial notebook. So basically, just going to go over those sequentially. So we're going to start with the explore dataset notebook. And then here, one thing that the output gave me the idea of doing was to actually try to find a data set that I could use for a clinical trial use case. So I went on the UCI machine learning repo and I found this heart failure clinical trials data set. So if I open this up here, this is the data set that I found, heart failure clinical records. And you see there's some description about what the data set is. And I believe the data set has 13 features. So age, anemia, creatinine, phosphokinase, diabetes, and so on, up to time and death events. And those are all of the features of the data set. So one of the things that I did was downloading that data locally. And basically, I have the data under the data folder. And just going through very quickly through the code, I do some data analysis, some EDA to see what is going on. I can see that it has all of the columns. They have no values. They have almost 300 rows. And then here at the bottom, I actually plot some interesting things about the data set itself. So here I'm plotting the distribution of the data.
Those are each of the features, right?
Well, not all of them, because some features I believe are not numeric. So, but
Okay.
those are all of the numeric features.
I see.
So we can see the distribution of age, the creatinine, phosphokinase, ejection fraction, platelets, and so on and so forth. So you can kind of get a feel for the data and the distribution of the data on the data set. And the next plot that we have here is a correlation matrix, which is really helpful in understanding how one feature is related to another. So I can see here, for example, that smoking has a positive correlation with sex, which leads me to believe that males tend to smoke more than females, or the other way around. I'm biased, so I think I'm going to say that males are usually smoke more than females. And there's some other correlations here as well. I think the biggest one is between death event and time, which I believe is as people get older, they also tend to pass away, which is a little bit morbid, but we can see that correlation here in the plot. And then the final plot that we have is a box plot. So again, all of those are the numerical features. And if you're not super familiar with box plots, they're basically just makes easy for us to see those distributions as well.
Yeah, these are all like a feature versus the death event. It looks like you've plotted.
Yeah, exactly. So all of those plots are the features versus the death events. And here we can see that, for example, when death event is 0, which is there's no death, the person is still alive. There's some outliers here, but it just makes very easy to see the distribution. And here, this line here at the middle of the box plots, it just shows how distributed the data is. If the line is towards the center of the plot, it means the distribution is more normal. But we can see, for example, this one is a little bit skewed, and this one as well. And the upper box here above the line is the third quartile, and the box below it is the first quartile of the distribution of the data. But then and the dots below and above the box plots are usually the outliers that are far away into the distribution. Okay, so let's go ahead and go to the next notebook, which is the simulate trials notebook here that I have. One idea that I got was to generate clinical trials for both patients and also the trials themselves. So Basically, this entire notebook, what it does is that it randomly generates trials for both patients and the trials themselves. So we can see here we have trial types, the trial names, some interventions. Those are going to be variables that we're going to be using in the code to randomly generate data. And I'm not going to go too much in depth into this, but basically what this function is doing is converting those variables into text and just randomly generating them. So we have here this eligibility criteria class. We have a trial class and a patient class. And then we have a function to actually generate the trial protocols, and then it uses those classes. And we are also doing that randomly. And as another thing, as you can see here, I have set a seed here at the top. So if you run this on your machine locally, you're going to get exactly the same results as mine if you keep your seed as 42.
Here you're not just generating like patient data itself, but you're actually generating the clinical trials. Is it doing both, or is it just generating like the clinical trial requirements?
No, that's a great question. So it's generating both. It's generating both the patient data and the clinical trials. For this particular function itself, is only generating the trials. We generate the patient data later.
Okay.
Yeah, so this is what the function is doing. And then here's where we're actually formatting and generating the patient data here. And then we just load the data and we run the function. And the results that we get is those JSON files. So we have trained patients and trained trials. So just taking a look at this, we have some data that was generated here. So we have each patient has an ID, demographics, and then some medical history. And all of this was randomly generated by just looking at our data set. So basically what we did, we took the features and the values in each of those features from the heart failure data set, and we used those as basically context to randomly generate dummy data for this project. So here is the patients, and then we also have the trials. We have both data for training and for testing. And the trials also have their ID, trial name, type, description, intervention, duration, eligibility criteria, and the eligible patients. So those are going to be the patient IDs that are within this trial.
Okay, so this is actually giving you kind of the answer because it has the training data, and saying that these are the patients that are matched to this this clinical trial.
To this trial, yeah, exactly. And then we do the same for the test trials, and there's also test patients here as well.
Great, yeah, and then these are, like you said, these are all using the data set that you found as like a way to generate more data.
Yeah, exactly. We're basically just leveraging the UCI data set to generate some data. And that's basically what we do in the notebook to simulate the trials. So in the next notebook for the patient trial matching, we're going to basically walk through a simple approach, basically a baseline approach to match the simulated patients to the clinical trials. And we're going to be using TF-IDF for doing that, which is basically an algorithm that is highly used for attack similarity. So the 4 things that we're going to be doing in this notebook, we're going to be setting up the project path. We're going to be loading and formatting the patient and trial data. We're going to be training TF-IDF vectorizer and computing the cosine similarity of that. And then we're going to be plotting that, the F1 scores, and visualizing how we do it. So here we are loading the paths. We're setting up some variables. And then here are going to be some utility functions that we're going to have on the next cell. So we're going to have a load JSON and a patient to tax and trial to tax functions. And those are going to be basically turning the JSON simulated data that we created previously into basically just plain English sentences that are going to be suited for the TF-IDF algorithm. And then I also added here, if you're new to natural language processing and you never heard of TF-IDF, I also added the Wikipedia link of how TF-IDF works. But basically, on a very high level, the TF means term frequency and IDF means inverse document frequency. And I added some of the formulas here of how to calculate them. But basically, that's how they do. The TF, it basically means how often a word appears in one document. And the IDF measures how unusual that word is across all documents. And we do that for every single word in every single document that we have. And then putting them together, we basically multiply them and we get this word scores. And then we can also identify basically a word score is high if it appears often in one document, but is rare across a collection of documents. And it basically helps us focus on distinctive words that are really that really tell two documents apart. So how dissimilar they are. So that's going to help us in classifying the patient data to the trial data. And that's basically the code that I have. Here's where we're doing the TF-IDF. So we initialize the vectorizer, we get all of the texts, we fit the text into the vectorizer, we get those two matrices, the P matrix and the T matrix, and we perform cosine similarity on those matrices. And then we are returning the matches and the similarities. And then we do some evaluation and we do some plotting.
And it looks like the evaluation, you have like true positives, false positives, so that you can calculate an accuracy score.
Yeah, so we're going to be using the F1 score, which is the harmonic mean between precision and recall. So that's what we're doing. Okay. We get the true positives, the false negatives. We calculate the precision, which is the true positives divided by the true positives plus the false positives. And we also calculate the recall. And then we calculate the F1 score and we return all of those metrics. And then the next cell, basically we just run everything. So we're just loading the data, we're running the functions to actually concatenate the data and get those sentences, and then passing them through the TF-IDF vectorizer, and then doing some plotting. So as you can see here, for the test trials, we only have 3 trials on our test data. And you can see that we perform not super well. I believe this trial here scored the highest at 8%. And I'll talk a little bit about basically what this means. So here we can see again, the F1 scores the harmonic mean between the precision and the recall. And basically what's happening in the plot itself is that the trial 001 achieved the best F1 score, almost 8%. And basically this means that the trial's wording overlaps is slightly better with the patient text, but it's still the score is very low, especially when it comes to the other 2 trials on the test data set. And then there's a few reasons why these numbers are so low. The sparse lexical overlap. So basically this just means that a patient's blob that was created, like the random text that was created, rarely contains exactly the same n-grams as the trial text. So basically the text from the patients is very different than the text from the trials. And then there's other reasons, maybe no structured checks, and also the threshold trade-off. So when we're training the TF-IDF algorithm, there's different thresholds that we can use. So maybe that's something that is happening too. And then one thing that I thought about doing, maybe how we could improve this score, is to actually use a model that was fine-tuned specifically on clinical trials. For that, I went on Hugging Face and I found this bioclinical BERT model that was fine-tuned on clinical trials. And this is going to be the model that we're going to be using on the next notebook.
Great. So that's like it's a small language model then, that BERT model that's been fine-tuned on clinical data?
Exactly. So it's a small SLM, or it's a SLM, a small language model, and it was fine-tuned on BERT. So it's basically just an encoder model. And here we're going to be using BERT, the fine-tuned BERT from Hugging Face that was fine-tuned on clinical data. So again, we're just importing some libraries and the project structure. And then there's a few helper functions here as well that I just want to quickly highlight. So there's going to be a function for patient to text. So it's going to mix the demographics, the age and gender, with the clinical history. And there is also a trial to text function that is going to pull each eligibility range and binary flag, and is going to join them with spaces. So this is what those functions are doing over here. And then for the bottom functions, the embed text, match by BERT, and then evaluation functions are going to be explained in this next cell here. So basically here, we're going to be doing four main things. We're going to be embedding each patient trial text with using the fine-tuned model. We're going to be computing the cosine similarity between the trials and the patient embeddings. And we're going to do a sweep of a similarity threshold to find the best average F1 score on the test set. And then we're going to be plotting that as well.
And these are the training and test set is the same training and test set that you used before, right?
Exactly. It's the same data we used before. So we have a fair comparison between this BERT model and the TF-IDF model. So here we just load the data. We load the clinical BERT model from Hugging Face. So we're using auto tokenizer from the pre-trained models on Hugging Face. We set the model to evaluation. We initialize some thresholds here that we're going to be using during that. And then we're also going to be using those parameters here, the threshold, the precision, recall, and F1 score during the evaluation. And then we're going to be plotting that. We're going to be basically getting some results and we're going to be plotting them. So we get those two plots here at the end. So we basically run the BERT model. We see that the best threshold value is 0.2. So that's also showed in this plots here. But one thing that was actually surprising is that this fine-tuned model actually performed worse than TF-IDF. And the reason for that, I also explain here at the bottom. The first plot, basically what it's showing is that we vary the cosine similarity cutoff, basically the threshold, from 0.2 all the way up to 0.8. And then with the lower threshold, allowed many patient trial pairs, so the recall was a little bit higher. And then above 0.6, basically there was no pairs that exceeded the similarity cutoff. So basically the key takeaway of the first plot is that clinical BERT's embeddings, pure similarity matching of these text fields, they only were able to achieve very low F1 scores, much lower than actually the TF-IDF. So this is basically the plots, and then the plot 2 shows the F1 scores. So we can see that I believe the same trial actually had the best score, but it's still it's very, very low. Basically 3% of F1 score, which is really bad. So basically the outcome of this experiment was that from the outputs of the prompts that I got from LobeChat, I was able to come up with a few ideas of a project that I wanted to do for this drug discovery application using LLMs. And I was able to create some synthetic data set by actually leveraging a completely unrelated data set on the UCI machine learning repo. I was able to generate synthetic data on that. And then I trained a TF-IDF vectorizer. And then I also was able to use BERT, a fine-tuned BERT model in clinical trials. The results are not good, but that's not because of the methodology itself, but probably because of the synthetic data generated, the synthetic data that I generated.
Yeah, so if we had more patient data that closely matched some of the clinical trials, then you might have more matches. But the thing is, with when you think about this kind of exercise, you don't necessarily want to have a lot of matches if the patient data isn't reflected well in the trials that you're trying to match them to.
Yep, exactly. So today, basically, just to recap what we did, we started out with a prompt on LobeChat. I got some code back. It gave me ideas on what to do next for this application. I went on the UCI machine learning repo, got a real data set, created some synthetic data, and then applied some NLP algorithms on that. And I learned a ton by doing so. So with that, if you'd like to reach out to us on Discord, feel free to do so. Go on the official Intel DevHub Discord server. Ben and I are available there, so feel free to reach out and drop a comment. And I'm also available on LinkedIn.
Great, yeah, and I'll echo what Murilo said. I'm happy to connect with you on Discord, and we'll make sure to leave a link for the Discord in the description, and happy to connect with you there. And then if I'm not available on there, just please reach out to me on LinkedIn as well.
Cool, awesome. Thank you very much, Ben. Thank you for joining us today. Hope to see you guys in the next one, and happy coding.